Good morning, everyone. As a project presenter, Yan Tong Lai. The paper I'm presenting is the automated mechanism design for integrating ad auction and allocation in feed. The authors of this paper are Xuejian, Wang, and others from China Meituan company from Beijing, China. Xuejian doesn't come here in person for the visa issue. Today's presentation is divided into 5 parts: background and motivation, key idea, methodology, experiments, and conclusions. In many e-commerce feeds, an order list mixed with several organic items and a pay-per-click ad is displayed for each page with requests of users, as is shown in this figure. If users click on the ad, the platform will charge the corresponding advertiser, which is a key source of revenue for the platform. Meanwhile, if users purchase the product in organic items or ad, the platform grows merchandise, GMV will increase. In practice, this list produced by ad auction and allocation processes directly determines the platform's revenue and GMV. More specifically, the ad auction determines which ad is displayed and the payment of the ad, while the ad allocation determines the display positions of the ad and organic items in feeds. Ad auction and allocation are interactive. Hence, mechanism designed for ad auction and allocation is to maximize platform revenue and GMV has become a very meaningful and challenging problem. The widely used method is to divide an auction and allocation into 2 stages. GSP is commonly used in the ad auction stage. Subsequently, during the ad allocation stage, the winning ads from the auction are dynamically inserted into the organic item list. This method of segregating the ad auction and allocation into 2 distinct stages face 2 problems as follows. Ad auction does not take externalities into account. Ad externalities generally refer to the impact of display position and context on its CTR. Traditional auctions, including the GSP, often do not consider externalities and obtain stable results based on the separated CTR assumption. However, in practice, the CTR of ad surrounded by organic items is impacted by its actual display position and context. Externalities result in complicated strategy competition among advertisers, precluding stable outcomes and social welfare optimization. Hence, when considering the externalities, traditional auctions are not suitable. For the ad allocation, using the winning ads payment is to determine display position dynamically. It's not IC for the ad. For the winning ad, even if its speed is increased, it does not secure a better position, thereby losing the opportunity to gain greater utility. This is because in the aforementioned ad auction, even if the winning ad increases speed, its payment remains the same, and thus the ad allocation winning ad to determine the display position is also inappropriate. Similarly, without any change in payment, the winning ad is motivated to increase its speed until it secures the best position and maximum utility. However, at this juncture, the GMV loss of the platform may exceed the increase in revenue. Therefore, designing a mechanism that integrates ad auction and allocation in feed should be considered. It needs to satisfy both IC and IR in the presence of externalities and maximize revenue and GMV. The integration of ad auction and allocation can be seen as a combination auction, CA, of ads and organic items, where the private value and bid of organic items on click can be assumed to be 0. It simultaneously obtains the ranking, payment and displaying position of ad. VCG, another classic mechanism, provides ideas for solving these problems, but VCG's expected revenue is lower than that of GSP, which is not acceptable for the platform. Inspired by a fine maximizer auction, AMA, we attempted application to integrate an ad auction and allocation. Moreover, the Mu network and Lambda network are modeled as deep neural networks and trained by an end-to-end learning methods referred to as MIAA. MIAA takes candidate ads and the ordered organic items that leads as input and outputs the optimal allocation by 3 modules. The 3 modules of MIAA are the externality-aware prediction module, EPM, the automated auction module, AAM, and the differentiable sorting module, DSM. Firstly, for each candidate ad, several candidate allocations are generated by inserting the ad in different positions of the ordered organic items list. This step corresponds to a time complexity of M times N. Then, EPM adopts a parameter sharing structure for all the candidate allocations. We use a self-attention unit to model the interaction between the ad and the organic items in the candidate allocation. EPM takes the allocation and 2 types of public information as input and outputs the PCTR for each item. Compared with pointwise models, listwise models capture the global externalities and output more accurate results, which can help the subsequent modules achieve better performance. This module selects the optimal allocation from all possible candidate allocations. Extending AMA into a deep automated mechanism, Mu and Lambda are modeled as deep neural networks, Mu network and Lambda network, to improve the expressive ability of ranking formula while guaranteeing IC and IR properties. Mu represents the strength of item buying capability and is dependent of the allocations. Each item has to represent its competitive ability. Lambda is an arbitrary function of the allocation. The social welfare of the allocation A is calculated as SW. The optimal allocation A is computed to maximize SW, Mu, and Lambda. The payment on click of the ad is the PI. Obviously, the process maintains the IC and IR properties of AMA. We aim to improve the efficiency and effectiveness of solving this mechanism problem in the end-to-end learning way. However, we're still faced with 2 challenges. The first one is the non-differentiability of the ranking process in auctions. The sorting operation is to obtain the optimal allocation leads to a non-differential process for the entire procedure. We use multi-classification model to conduct a continuous relaxation of sorting operator in the mechanism. Given the allocations set SW, the vector of the allocations is mapped by the softmax function. And the second one is the lack of user real behavior feedback. We use the PCTR and predicted GMV indicators to simulate user behavior and calculate the performance metrics at the allocations, which are then used for feedback training. The expected revenue and GMV of the allocations are calculated by ref and GMV. Finally, the overall optimization goal is to maximize reward Mu and Lambda. This loss provides direct feedback for training Mu network and Lambda network, which is a partial differential method. We evaluate the effectiveness of the proposed mechanism MIAA with the aim of answering the following questions. Question 1 is, compared with the point-wise PCTRs, how does our list-wise model perform in terms of CTR prediction? The question 2 is, compared with widely used ad-auction and allocation mechanism in the industry platform, how does our mechanism perform in terms of platform revenue and GMV? In the offline experiments, we provide empirical evidence for the effectiveness of our mechanism on both public and industry datasets. The public dataset is the Avato dataset used for the Avato contest at clicks competition of Kaggle. The industrial dataset is collected under GSP auction and fixed positions on Meituan retail delivery platform during December 2023. On the public Avato dataset, we construct point-wise model and list-wise model of EPM. Only the first position and fourth position in this list have real user click behavior data that can be used to evaluate the performance of this model. For all positions in allocation, the list-wise PCTR in EPM improves the AUC by 0.0036 compared with the point-wise PCTR, and its PCOC is closer to 1. On the Meituan industrial dataset, the point-wise PCTR by DIM model is already included. Obviously, considering the externalities, etc., the display position and context of the ad, the list-wise model in EPM performs better on AUC and PCOC metrics than the point-wise models on both the public dataset and the Meituan industrial dataset. MIAA achieves the highest revenue and GMV, outperforming all baseline mechanisms. Compared with GSP and fixed position, MIAA achieves significant improvements as items with higher eCPM or GMV obtain better positions and the payment of ads is increased. Score-weighted VCG achieves maximum PRPM without considering the loss of GMV. Compared with IAS, MIAA, which considers externalities, achieves higher PRPM and PGMV. We conduct online A/B tests with 5% of whole production traffic from October 15, 2023 to December 15, 2023. The online tests make it difficult to evaluate the proposed mechanism's incentive effect on advertisers' buying. We only focus on the performance of revenue, GMV, RPM, and GPM. The proposed mechanism achieves the highest promotion for revenue, GMV, RPM, and GPM. Conclusion, we propose a deep automated mechanism for integrating ad auction and allocation that satisfies both IC and IR in the presence of externalities and maximize revenue and GMV. We use a list-wise model for global externalities modeling. We use an automated mechanism based on deep neural networks to select the optimal allocation from the candidate allocation set in an end-to-end learning way. The ranking, payment, and display position of the ads are determined at the same time. For the future research, Maltese loads ad auction and ad allocation. For the second one is the user real behavior feedback and list-wise model generation, partial differentiable, the uplift effect of advertising when it overlaps with organic items. Thank you so much. If you have any questions, you could contact the first author by the email.
All right, let's thank the presenter and thank you.